Hey everybody, welcome back. This is Math 35 at College of the Sequoias, and this is College Algebra. And today we're going to finish up Chapter 2. This is Section 2.8, and what we're covering is function operations and compositions. And compositions. Now, I really like this topic because it points out just how lazy mathematicians are. This is how lazy mathematicians really are. In the following, compare the difference between the two sides. Two sides of the equation. Okay. And I'm going to start off, before I give the equation, what we're given. We are given two functions. We're going to use f of x and g of x. So here is your magic equation that shows just how lazy mathematicians are. F of x plus g of x equals f plus g in parentheses like that of x. Now just stop and observe that and see just how much we're saving. Because the left side is pretty clear what's going on. We're adding together the two functions. What do we save? I've got this f here, and that matches that f there. I've got a set of parentheses that matches this set of parentheses. I've got an x in here. I've got an x there. I've got a plus sign. There's a plus sign there. I've got a g. There's the g. I've got a parentheses and another parentheses. Those are right there. In fact, the only thing that this notation saves is this. This is the only character not in the right side. There's only one x on the right side, not two. And yet, until you learn how this works, a lot of students get confused by this. So it just takes some practice. I would do flashcards. That's my pro tip. Pro tip for the following: make flashcards of these operations. Until you have them memorized. And memorize, that memorizes. We're actually going to look at 4 of them before we do the composition, and so let's just depict what they are. The one I gave above is the sum. F of x plus g of x equals f plus g of x. And subtraction is just addition of the opposite, but if you want to call it something different, the difference of two functions, f of x minus g of x, is just like that, the sum. We just changed the plus to a minus. On the product or multiplication, we have f of x times g of x. And when we do it here, we put fg x. I am going to point out, don't do f dot g x. Don't do this one. And the reason why is it looks like composition, as you'll see when we get to composition. It looks like the composition of two functions. The dot means multiplication, but when we do composition, we use a little small circle, and a small circle looks a lot like a dot. So you're better off just doing FG like that. Two things touching each other like that are multiplied together. And finally, we have our quotient. F of x divided by g of x is f divided by g of x. So again, all we're really saving is the x. On product, we save the multiplication symbol as well. And of course, on this one, g of x cannot equal 0, obviously, because we can't divide by 0. All right? And let's just get started. Before we start working on examples, I do want to point out what the domain is when we have composition. Domain is the intersection or overlap of the two functions' domains. The domains of the two original functions. And let's look at our first example. Our first example, we are going to have f of x equals 3x minus 4. And g of x equals 2x squared minus 1. And oftentimes when we're looking at working with these operations, we're looking for a specific value. So in our first example, we're going to look at f plus g of 0. And recall what that means is f plus g, where x is evaluated at 0. Now you have two options here. Two options. Do f of 0 plus g of 0, calculate them separately. Let me change that to do f of 0 and g of 0, and then add. Or add the two functions first, then evaluate at x equals 0. And I'm going to add more to that, but I want to go through them and do them, show what I mean by that. So first option, option 1, I'm going to do f of 0. F of 0, I'm just plugging in 0 for x. 3 times 0 minus 4 is minus 4. And g of 0 is 2 times 0 squared minus 1, which is minus 1. So f of 0 plus g of 0 equals negative 4 minus 1, which equals negative 5. Which means f plus g of 0, the notation they gave us, is negative 5. Now let's take a look at option 2. F plus g of x equals f of x plus g of x. And f of x is 3x minus 4. And g of x, I'm going to put in parentheses. The reason why I'm doing it is it doesn't really matter what the plus sign, but if you're doing subtraction, you're going to need to distribute the subtraction. And I'd rather you be in the habit of it now. In fact, maybe we should put parentheses around that one. So f plus g of x equals, I'm going to put them in order, descending order by exponent. I've got 2x squared, and then I've got plus 3x minus 5. Finally, I evaluate that at 0. 2 times 0 squared plus 3 times 0 minus 5. F plus g of 0 equals negative 5. Now, you might say, and I would agree with you, adding them together first just makes more work. Okay? There is a benefit to it, though. Option 2 adds more work initially. But if you need to evaluate more than one x value, this saves time. Okay? So if you had to do a bunch of them, it will save you some time. All right? That's the sum, and it's pretty straightforward. It's not really all that challenging. You've added polynomials together before. This isn't any different. You've evaluated functions. That's not any different. The only thing that's different, that's new, is this notation, this f plus g of x. And if you flashcard that, this isn't really hard. All right? Let's look at a next one. I'm going to use the same ones. I had f of x equals 3x minus 4. And I had g of x equals 2x squared minus 1. And let's take a look at f minus g of x. Now here, I don't give you x and value to put in. I did not give you a value to evaluate x at. So we literally just have to do it as it is. This is f of x minus g of x, and we got to stick with the x's. So we've got 3x minus 4 minus 2x squared minus 1. Then I can dump the parentheses on the first one without problem. On the second one, though, I need to distribute the negative sign, which changes the sign of everything inside. This becomes negative 2x squared, and negative times negative 1 becomes positive 1. Finally, I put everything together in descending order and combine like terms. F minus g of x is, I've got negative 2x squared plus 3x, and then negative 4 plus 1 is negative 3. And I mentioned domain earlier. Let's just take a look at the domain. The domain of f of x is, it's a line, so all real numbers work. The domain of g of x is a parabola which has a limit on the range, but not on the domain. It's all real numbers. So the intersection, the domain of f plus g of x and f minus g of x, and even fg of x, or f times g of x, is all real numbers. Or negative infinity to infinity. Now, the quotient will be different. I'll cover that one in a second when we get to it. All right, so that's the subtraction one. Let's take a look at fg of x. So here we're going to do the product one. So this is f of x times g of x. And that's 3x minus 4 times 2x squared minus 1. And now we've just got two parentheses multiplied together. We just distribute, or FOIL. We start off with the first terms multiplied together. 3x times 2x squared is 6x cubed. Then we do outside. 3x times negative 1 is negative 3x. So I'm going through FOIL. First, outside, inside, last. First, outside, inside, last. So we got our first, our outside, our inside is negative 4 times 2x squared is negative 8x squared. And then our last, negative 4 times negative 1 is plus 4. That's an acronym that's easy for people to remember on how to distribute these. If we write them in descending order as we should, I've got 6x cubed minus 8x squared minus 3x plus 4. Now, if I asked you to evaluate this at, let's say, -2, let's give you some practice. In fact, I want you to do that. Find fg at -2. Pause it and go ahead and work that out. If I do it right here, fg of -2, I've got 6 times -2 cubed minus 8 times -2 squared minus 3 times -2 plus 4. -2 cubed is -8. And -2 squared is positive 4. -3 times -2 is 6 plus 6, and then I've got plus 4. 6 times -8 is -48. -8 times 4 is -32. And then I've got plus 6 plus 4 is plus 10. 48 and 32 added together is 80. So I've got -80 plus 10 is -70. Alternatively, you could have gone back and done f of -2 is 3 times -2 minus 4 is 3 times -2 is -6 minus 4 is -10. G of -2 is 2 times -2 squared minus 1. -2 squared is 4 times 2 is 8 minus 1 is 7. So fg of -2 is -10 times 7 is -70. All right. Got it. It's the same answer both ways, right? So those three all had the domain is all real numbers. Let's take a look at the quotient. And I'll rewrite them again. F of x is 3x minus 4. G of x is 2x squared minus 1. So I got, if I look at f divided by g of x, this is f of x over g of x, which is 3x minus 4 over 2x squared minus 1. And this doesn't simplify. Simplify. So that's all it is. If I wanted f of g of 0, I got 3 times 0 minus 4 over 2 times 0 squared minus 1 is negative 4 over negative 1, which is positive 4. If it had simplified, it would have actually made plugging or evaluating in easier. So we found the domain for everything else. Now we need to find the domain here. What's the domain? Well, f of x can be all real numbers, g of x can be all real numbers, but when we divide f of x by g of x, we have to restrict g of x to not equal 0. And the easiest way to do that is to figure out what that is by setting it equal to 0 and solving. So set g of x equal to 0 and solve to find our bad juju numbers. Bad juju numbers make the denominator 0. If I set g of x equal to 0, I've got 2x squared minus 1. I could use this 0 here, but a lot of people like having the 0 on the right, so I'll do that. Start off by adding 1 to both sides. You get 2x squared equals 1. Divide by 2. And I get x squared equals 1/2. And then I take the square root of both sides. And I get x equals plus or minus the square root of 1 over 2, which is 1 over the square root of 2. We don't want to leave it like that. We don't like having radicals in the denominator, so we'll multiply by the denominator to clear them. And so I get x equals plus or minus the square root of 2 over 2. That's the problem. These are domain violations. And there's two of them, negative square root of 2 over 2 and positive square root of 2. So x cannot equal that. If we wanted to write it in interval notation, it's negative infinity up to negative square root of 2 over 2. And then we do a parentheses because we're not including it. In union with parentheses again, we started right back up, negative square root of 2 over 2. This shows us that only negative square root of 2 over 2 is out, up to positive square root of 2 over 2. And then we'll do union again, square root of 2 over 2 to infinity. That is the long way of saying x cannot equal plus or minus the square root of 2 over 2. All right, so, and actually, let me write that out. This is the long way of saying x cannot equal plus or minus the square root of 2 over 2. All right, let me give you guys some to try, and we're gonna choose different ones. Different functions, I mean. So your turn. F of x is x squared minus 3x. G of x. Oh, let's see, what do I want to do? Let's go with 4x minus 12. Find f plus g of x, find each of them. F minus g of x, f times g of x, and f divided by g of x. And their domains. Please pause the video and give yourself some practice doing this. All right, so I'm going to assume you paused it. Let's take a look at them. F plus g of x. I've got x squared minus 3x plus 4x minus 12. If I add those together, x squared, negative 3x plus 4x is plus x, and then minus 12. F minus g of x, x squared minus 3x minus 4x minus 12. I'll distribute the minus sign real quick before I add them. Negative distributed to the 4x is negative 4x, and negative distributed to the negative 12 is plus 12. And then I combine like terms. We'll take a look at fg of x. X squared minus 3x times 4x minus 12. I get 4x cubed. I'm changing the order. I'm going to do the x squared one next. I got negative 4x cubed, negative 12x squared, and another negative 12x squared. And then negative 3x times negative 12 is plus 36x. So this is 4x cubed minus 24x squared plus 36x. Okay. And then each of those, f of x and g of x are parabolas and lines. So f of x and g of x have domains of all real numbers, or negative infinity to infinity, which means f plus g of x, f minus g of x, and fg of x all have the same domain. Domain is all real numbers. And now we'll look at f divided by g of x is x squared minus 3x over 4x minus 12. Before I simplify, I'm going to find my bad juju number. g of x, which equals 4x minus 12, cannot equal 0. So I add 12 to both sides, I get 4x cannot equal 12. Divide by 4, and I get x cannot equal 3. If I factor this, this does clean up. You should always factor it to check. X times x minus 3 is that. And I've got 4 times x minus 3. The x minus 3's cancel, and I'm just left with x over 4 or 1/4 x. Now, even though 1/4 x does not have a problem with the domain, by itself, this would have a negative infinity to infinity by itself. But this still applies. Even though it canceled out. Even though it canceled out. So x cannot equal 3. The domain there, if we do it in interval notation, negative infinity to 3 in union with 3 to infinity. This is a very, very, very important topic. You will be taking trigonometry soon, hopefully next semester, staying on sequence. And then after that, you'll be hitting calculus. And this shows up in calculus. And I'm going to even show you where it shows up. I want you to know that this is important. In calculus, derivatives are a super huge and important topic. I'd say about 40% of all the work, of all calculus. And if we recognize that integration is doing derivatives backwards, it's even higher. So, or higher. This topic is that important. Derivatives are developed from the difference quotient. Derivatives come from the difference quotient. And what that is f of x plus, f of x plus h minus f of x divided by h. And sometimes they use, or h is sometimes written as delta x, which would make this f of x plus delta x minus f of x over delta x. So let's just look at a practice example. Let's say f of x equals 3x squared minus 2x plus 4. And let's find the difference quotient. We need to figure out what f of x plus h is. And I think using h is easier than using delta x, especially when you're working it out. So I need to do 3 times x plus h squared. Everywhere I have an x up here, I'm going to plug in x plus h. Minus 2 times x plus h plus 4. This becomes 3 times, remember that is x plus h times x plus h. And you got to multiply it out. So there's an x squared, there is 2hx, and then there's plus h squared. Minus 2x plus h plus 4. I distribute, I've got 3x squared plus 6hx plus 3h squared minus 2x minus 2h plus 4. Finally, we have f of x plus h. We gather like terms. I've got 3x squared. Do I even have any like terms? There are no like terms, are there? Nothing's like. No like terms. So that is f of x plus h. Finally, we're going to do f of x plus h minus f of x over h. I've got 3x squared plus 6hx plus 3h squared minus 2x minus 2h plus 4 minus f of x, 3x squared minus 2x plus 4. Let's just do the f divided by h last. So f of x plus h minus f of x cleans up to, this becomes negative 3x squared plus 2x minus 4. That last set right there, and now I can combine like terms. 3x squared minus 3x squared go away. So I've got 6hx plus 3h squared. The negative 2x and plus 2x cancel each other out. And then I've got minus 2h. And I've got plus 4 and minus 4. Those cancel each other out. So if you've done the difference quotient correctly, everything that has just x's in it, no h's, goes away until you divide by the h. When you divide by the h, you get 6x plus 3h minus 2. In calculus, to get the derivative, then you'll let h equal 0. And you'll get 6x minus 2 for the derivative. But the point is, you use these functions, subtraction of functions. This comes up. Finally, let's talk about composition of functions. All right. All right. So composition of functions. We have f og of x. What this means is we're going to take f of x and we're going to put g of x inside of it. G of x goes inside f of x. And this is different than doing the other way around. We have that, f goes inside g. And the way we tend to say this, we will say f of g of x. That's how we verbally say it. And when you're lazy, and a lot of people will just say fog x, the slacker or lazy way. is fog x, like fog, foggy weather. But you want to try to avoid that because that can be confusing. F of g of x is consistently said by everybody. So let's take a look at them. Let's just take a look at an example. F of x equals the square root of x plus 4. G of x equals 2 over the square root of x. And we're going to do fog, or f of g of 2. And let's take a look at g of f of 2. Okay, so two outcomes here. F is the square root of x plus 4, g of x. So this is saying f of g of 2, which means we start with g of 2. G of 2 is 2 divided by 2, which equals 1. When I plug that in, now what I have is f of 1. Well, that's the square root of 1 plus 4, which is the square root of 5. So f of g of 2 equals 5, square root of 5. Now, if you look at g of f of 2, this is g, and then f of 2 is inside. We'll do f of 2 first. F of 2 is the square root of 2 plus 4 is the square root of 6. So now what that says is we're going to evaluate g at the square root of 6. And I get 2 over the square root of 6. And I'll rationalize it. And I get 2 root 6 over 6, which simplifies to 1/3 root 6, or root 6 over 3. And that's g of f of 2. Notice they are not equal. F of g of x does not equal g of f of x unless a really unique circumstance pops up. Rarely does it equal each other. Does f of g of x equal g of f of x? Since I'm saying it, maybe I should write it down. Especially if I have students that are hard of hearing or anything like that. Got to keep that in mind. So let's do another one, and we're going to change it up a little bit. So I'm going to make f of x equal the square root of x minus 1. And g of x is 2x plus 5. We want to find f of g of x and g of f of x and their domains. And the way we find the domain, so finding the domain of these, the domain of a composition, of functions. Identify the domain of the inner function first. And the reason why I say this is this restriction, if there is a restriction, this restriction, if it exists, if there is a restriction, it might be all real numbers. If it exists, has to hold even if the restriction isn't present after we combine the functions. I guess I didn't need to say an A. That's just the rule. Identify the domain of the inner function first. So let's take a look at f of g of x. I have the square root of 2x minus, or x minus 1. And where I have x, I'm going to put in g of x. 2x plus 5 minus 1. This ends up being the square root of 2x plus 4. Now the domain, g of x is all real numbers because it's a line, so we're good there. So then we just got to find the domain of f of g of x. Domain of f of g of x. When you have a radical, the radicand has to be greater than or equal to 0. So if I subtract 4 from both sides, I get 2x is greater than or equal to 4. And finally, I divide by 2, I get x is greater than or equal to 2. Which means the domain is 2 to infinity. We include the 2, we give it a bracket. Wait, that's a -4. Look at me making a mistake. That's a -4 right there, and that makes that a -2. Now we'll take a look at g of f of x. F of x is the square root of x minus 1. It goes inside wherever there's an x in g of x. And that actually doesn't clean up either at all. It might be easier to write 5 plus 2 square root of x minus 1, simply because then we know the 5 is not inside the radical sign. So first we find the domain of the inner function, the one that goes inside f. The domain of f, well, f of x is the square root of x minus 1. We need x minus 1 to be greater than or equal to 0, which says x is greater than or equal to 1. And so even though g of x, this is going to have a similar domain, right? That's still the only spot that has a violation. G of x didn't have a problem, so that's the domain restriction. It's got to be greater than or equal to 1. All right. This composition is very, very important, also in calculus. And I'm going to show you why. Got an itch, sorry, hold on a second. All right. So let's talk about how this is important in calculus, why you need to know this. This is very important in calculus. For something called the chain rule. And I'm just going to give you an example rather than explaining all the calculus stuff behind it, because that's for a later date. If I have f of x equals x to the fourth, and g of x equals 3x plus 2, and I have h of x equals f of g of x, which means I'm going to put 3x plus 2 into f. Okay? Again, that's f of g of x. Now, in calculus, the derivative is written a couple ways. They will say h with a, that's called h prime of x, or, that's good enough. I don't want to show you more. The chain rule ends up doing this. H prime of x, since h of x equals that, it's going to be f prime of g of x times g prime of x. Okay? You're not being, important to note, you're not being tested on this. But notice the relationship right here. The derivative of a composition is the derivative of the whole thing that's what that part is. That's that part. Times by the derivative of the inside. Inner function. And that's, the inner function was g of x, the derivative is g prime of x. And that would end up using the difference quotient we did earlier. And so you'll get used to doing this a lot. Again, I am just pointing this out for its importance. In calculus, you are not tested on this. And you don't need to know it right now. But I want you to understand when I'm teaching stuff, I like to point out when you're going to see it again. Because some people go, what is this good for? And well, in and of itself, compositions, it really doesn't, it's kind of, I would have to work hard to come up with a word problem that goes with it. But when you get to calculus, plenty of real life problems are solved using calculus. And these are the tools that we use when we do calculus. All right. Let me give you guys one to practice on. You try. And we're going to make f of x equal to 5 over x plus 4. And g of x equals 2 over x. And find f of g of x. All right, so I'll assume you're pausing it and working on it. Fog x is f of x evaluated with g of x. So what I need is f of 2 of x, 2 divided by x. So I've got 5 over x plus 4. And I put a 2 of x in there. I've got fractions inside of fractions. This might be easier if I multiply the top and bottom by the inner fraction, the denominator of the inner fraction. We covered doing this in the practice, the review section, chapter R. Distributed on top, I get 5x. If I distribute it to each of these, 2 times x, or 2 over x times x is just 2. And then x times 4 is plus 4x. So f of g of x equals 5x over 4x plus 2. And those don't simplify because the top's got an x and the bottom does not. Everything has a bottom. Now calculate the domain. What is the domain of the composition? Well, g of x is 2 over x. The domain restriction here is, since we've got a fraction with a variable on bottom, x cannot equal 0. And then I look at f of g of x. We have a domain restriction here also. 4x plus 2 cannot equal 0. And if we solve for that, we get 4x cannot equal negative 2. So x cannot equal negative 1/2. Both restrictions apply. Even though 5x over 4x plus 2 doesn't have a problem at x equals 0. It violated g of x, though. And since it's a composition of the two, we can't have it. And where we remember, sometimes when we were evaluating stuff, what this is saying is I cannot say, I can't do f of g of 0 because that's f of g of 0, and this doesn't work. Even though if I plug in 0 here, I'd have 0 over 2, which is 0. All right? There are circumstances I told you it was rare. There are circumstances when f of g of x equals g of f of x, or if I write it in its full written out form, this is when, or this occurs, this happens when f of x and g of x are inverse functions of each other. And I believe we do this in chapter 3. We cover this later in the course, inverses. I believe in chapter 3. All right, that wraps up what you need to know for 2.8, and that's the end of chapter 2. We will have a midterm shortly on this. I won't say how far away, because if this is a later semester, you might be doing this at a different time, but it's coming up in the near future. If you're watching this, you're probably a week out, hopefully a week out of when we're going to do the midterm. Peace. Everybody take care.